Hello, my sweet chemists. Today we're going to be talking about using measurements and different types of measurement. Okay, go. We'll see. So we're going to talk about accuracy versus precision. A lot of times people get these two terms confused. Accuracy is how close a measurement is to the accepted value, and then precision is how close a series of measurements are to each other. So in other words, to check precision, you probably need to check the range. The smaller the range, the more precise it is. I think a lot about throwing darts, and in fact that's an analogy that we'll use. So accurate is correct, precise is consistent. So if we look at dart throwing, and I am no dart thrower, or whatever it's called, darter, whatever. If we look at these three examples, the first one on the left shows bullseye, and I think in my way of playing darts, if I hit bullseye, I'm dropping the rest of the darts and walking away because I just won. But what we see here is if they're aiming for bullseye, they have three of them, all three of them hit the bullseye, and let's say bullseye is what they were aiming for, then that is good accuracy. They did what they were supposed to do. They have good precision because all three of those darts are very close together in proximity. The middle one, this is probably, well, that's not closer to what I do. People have to, wear goggles around me. But if we look, they didn't hit the bullseye, so it's not accurate. So the accuracy is poor, but they are still grouped very close together in proximity. So that means that they have good precision. And then the one on the right, they didn't hit the bullseye, poor accuracy. The darts are all over the place, poor precision. Okay, so there's two types of errors that we can have. If we have random errors, we don't know how they're happening, they're going to reduce our precision. But if we have systematic errors, meaning we're doing the same thing wrong every single time, that's going to reduce our accuracy. All right, so when we're reporting measurements, this is where we're going to get into some nitpicky things. So we need to report what we know with certainty. So if we look at this nail and we look to see what is the length of the nail, and we look and it's definitely 6, so we look at the digits that we're absolutely sure about. Definitely 6 we're sure of, definitely 3, but are we sure about, I know it's in between 3 and 4, but are we sure that that is 5? No. I mean, we can guesstimate it, but we're not absolutely sure. So this is the one that we're going to do as an estimation. So 6 and 3 we're absolutely sure about, and then the next one will be our estimated. So that's how we get 6.35. Same thing with graduated cylinder and water or any kind of liquid. I'm sure that you've seen a meniscus. Water is not perfectly flat in a graduated cylinder. It has that curved line. It's the meniscus. And so if we look at this, you need to see what is the volume. So first of all, we need to look at what the graduations are, and it's going from 10 to 20. So each one of these lines must be 1. So are we measuring it here or are we measuring it here? You're always going to measure at the bottom of the meniscus, so we're measuring it right here. So now we're going to count 10, 1, 11, 12, 13, 14, 15. So it's 15 milliliters. We're sure about that. Is it right on the line? It probably is. So can we for sure tell us what the next digit would be? We can't. We don't have enough graduations for that. So 15 is our absolute, and then we guesstimate the next digit, which would be 0.0. All right, so if you were trying to figure out some volume in, we've already talked about this, that you wouldn't use a graduated cylinder, you wouldn't use a beaker, you'd use a graduated cylinder. And it's because a beaker is not accurate. It's just for holding stuff. We just don't measure in a beaker. We're going to use graduated cylinders that it will be a more accurate reading for any liquid. So now let's talk about percent error. This indicates an accuracy of a measurement. So we want our measurements to be accurate. How are we going to determine that? Well, there is a literature or a accepted value for whatever it is that we're trying to measure generally. So you have your measurement, which would be your value, and you subtract it from the accepted value, and then divide it by the accepted value, multiplied by 100 gives us the percent. That is our percent error. So let's look at an example. A student determines the density of a substance to be 1.40 grams per milliliter. Find the percent error if the accepted value of the density is 1.36 grams per milliliter. Well, number one, we can say that they're not accurate. We don't know enough information to see if they're precise, how many times that they measured it. So our measurement was 1.40 grams per milliliter. We subtract that, and again, it's the absolute value, so we won't have any negative numbers. We subtract that from the accepted value, which was 1.36 grams per milliliter, and then divide it by 1.36 grams per milliliter, and multiply it by 100, and we get 2.9%. Not too bad. So when we talk about significant figures, this will be something that we talk about for the rest of the year. This is something that we will consider in every single calculation that we will do for the entire rest of the year. Sometimes they're known as significant digits, sig figs, sig digs, that type of thing. But this is where we start looking at our numbers that we get with more scrutiny. In chemistry, our numbers are measurements. They're not made up numbers. They're not imaginary numbers like they might be in math. And they must reflect the accuracy of the equipment that we use to get those measurements. So for example, we're not going to use all the numbers that we see in a calculator. So I gave an example. If I did this math, I'm not going to just write down all of these numbers. That would not be showing the accuracy of our measurements. So it actually would be 7.85 times 10 to the minus 9, and I'll explain that in a second. So we are going to explore lots of other examples, and I promise you we'll get lots and lots of practice throughout the year. You may not be perfect with them when we start. You will definitely be really good by the end of the year. So accuracy of a measurement is why we talk about significant figures. So hold on, that was bad. So our paper clip here is 2.35. Because our measuring tool, our ruler, we could only go to two places, two digits that we're certain about. And again, remember that last one we have to guesstimate. So we're certain about the 2.3, and then we look and it's, maybe a little bit more than half. I think it's probably a little less. But that's the one that we're guesstimating. And in a lab group, that's when you would talk about it and decide between y'all. So it is really important to be honest when reporting our measurement, and so it doesn't appear to be more accurate than the equipment used to make the measurement. I give the example, there's an example there, I give the example of calculating something that we measured mass for. And let's say you did your calculator and you ended up with, I don't know, 10 digits, and you put them all down. What that indicates is that your balance was accurate to 10 digits. Y'all, we can't afford that kind of a balance. It's just going to be too expensive. So we have to limit the digits that we have, that we report, according to the equipment that we have. Okay, so let's practice measuring. So we know that if we look at the top one, and we're using this ruler, we come up here, we're like, well, that's about, we know 4. We don't have any other graduations or any other lines. So we could say, oh, it's about 4, and then guesstimate 0.5. On this one, we have more lines, and we can tell that it's 4.5, and then we'd have to guesstimate on the next one. I don't know why that one came up separate. And so it is a little bit more, actually I don't like that example. Okay, moving on. So here's the significant figures cheat sheet, and you will have these in your packet. So we're going to count all numbers except leading zeros, the zeros before numbers like in a decimal, or trailing zeros when there isn't a decimal place. Those are the big ones. So I'm going to put all of these up here. So here are the rules. All non-zero digits are significant. So if it is a non-zero digit, it is definitely going to be significant. So these rules are on page 11. If those zeros are sandwiched between non-zero digits, they are significant. So the example would be 1,001. So those zeros in between those ones make them significant. Zeros to the right of a decimal and to the right of a non-zero digit are significant. So if we look at this one, the 0 is to the right of a non-zero digit and to the right of a decimal place, then it is significant. Zeros between non-zero digit and a decimal in numbers greater than 1 are significant. So if it was just 100 without a decimal, it would be 1 sig fig. Because there's a decimal after that last 0, that makes it 3 significant figures. Here's our disclaimer. Just because it's not significant does not mean it's unaccounted for. It still makes a difference. It's just not significant. That our sig figs can keep track of the accuracy of our measurements, and they cannot be more accurate than our equipment. So let's do some examples. So number 1, 23.50. There are 4 significant figures because this 0 is to the right of a non-zero digit and we can see a decimal. Number 2, there are 3 significant figures because this is a sandwich 0. It is sandwiched in between 2 non-zero digits. Number 3, 3 sig figs. This 0 is not significant because although it is to the right of a non-zero digit, there is no decimal that we can see. And then number 4, 2 significant figures. The zeros in front are not significant because they are leading zeros. The 0 behind the 8 is significant because it is to the right of a non-zero digit and we can see a decimal in the number. So one of the ideas that I have, and examples I have for leading zeros, is if this is my bank account, where does my money start? Is my money starting here at this 0? No. Is my number starting here at this 0? Not yet. This is where my money starts. And so that's where my significant figures begin as well. All right. So now you have your practice, and then you'll get with me and we'll see if we are agreeing on them. So let's talk about scientific notation. I find that a lot of students have come to us having kind of learned scientific notation, having not. I know I didn't learn it very well when I was, well, before actually. So what scientific notation is putting really large numbers into a more manageable figure that we can deal with. So for instance, 65,000 kilograms would be 6.5 times 10 to the 4 kilograms. So when you convert into scientific notation, you move the decimal until there is just one non-zero digit to its left. The number of places moved equals your exponent after the times 10. The sign of the exponent is going to be positive if the original number was greater than 1. It's going to be negative if the original number was less than 1. And you're only going to include significant figures, so we have to count our sig figs before. So for instance, we're going to move this decimal, the invisible decimal, till there's one non-zero digit to the right.